In this video, we're going to begin talking about elementary row operations for matrices with the hope of being able to sort of streamline the process of Gaussian elimination. So recall from section 7.3 that there are actually three operations which gave us an equivalent system of equations. Those three were that we could interchange two equations, and also that we could multiply an equation by a non-zero constant, and finally we could add a multiple of an equation to another equation. Now in matrices, these actually correspond to what are called elementary row operations. And so going through these, our row operations are going to be very similar. Namely, just as we can interchange two equations, we can also interchange two rows. And just as we can multiply an equation by a non-zero constant, we can also multiply a row by a non-zero constant. And finally, just as we can add a multiple of an equation to another equation, we can also add a multiple of a row to another row. So we also say that two matrices are row equivalent when one of the matrices can be obtained from the other matrix by only using a sequence of those three elementary row operations. Okay? So to get a better feel for the elementary row operations and how they sort of they interact with matrices, let's go ahead and try an example. So here, in each of these situations, going from the matrix on the left-hand side to the right-hand side, we performed one elementary row operation. And so we're going to try to figure out which one it was. In this scenario, here, we notice that the two matrices look the same, except these two rows going from here to here got swapped. And namely, that is exactly what we're doing. We're swapping row 1 and row 2. Okay, so that's the interchange. That's the first thing we can do. That was the first operation we were allowed to do. Here, going from the left-hand side to the right-hand side in part B, what we see here is this row is the same, this row is the same in both of them, but the top row is different in each one. And so we say, well, what happened here? Well, we see here that 1 is half of 2, negative 2 is half of negative 4, 3 is half of 6, and 1, there should be a negative 2 right here. Sorry about that. Typos happen. But negative 1 is exactly half of negative 2. So indeed, this is actually going from this side to this side. What we did is we took R1 and we made R1 into 1/2 R1. Okay? Or I guess I would say 1/2 R1 became R1. Okay? And so, and then finally, for our last one, we see here that the top two rows are the same in each of these, but in the bottom row, something is different. Well, this is not, so this wasn't a swap, right? Because there's not two swapped. And it cannot be a multiple, this cannot be a multiplication. And the reason it can't be a multiplication is the only way to go to 0 from 2 is to multiply by 0, but if we had multiplied the whole row by 0, this 1 would have become a 0, and all of these would have been 0. So that can't be right. So it must be the third operation. We must have added a multiple of one row to this row. Well, the only one we possibly could have done is the top row to get rid of that 2. Again, you should be thinking of Gaussian elimination here. And to eliminate that, we would need to take negative 2 times the top row and add it to the bottom row to be able to get rid of that 2 there. Namely, it appears that we took R3, we took we took negative 2 times R1 and added it to R3 to get a new R3. let's see if that really does work. So if we take -2, so we already checked the first one, but if we take -2 times 2, we get -4. Adding that to 1 is indeed -3. -2 times -4 is +8. Adding that to 5, you get 13. And taking -2 times -1 is +2. Add that to -2, and again, I think I have a typo here. Yes, this was supposed to be a 3 up here. Sorry about that. So taking -2 times 3 is -6. Add that to -2, and we have -8. So this does in fact work. And now it's time for you to try an example. So go ahead and identify the elementary row operation performed to obtain the new row equivalent matrix. On the count of 3, I will reveal the solution. 1, 2, 3. So you can see here that the only row that's different between these two matrices is the middle one. So row 2. And to go from here to here, again, we notice that the 3 became a 0, but nothing else became a 0, so it couldn't be a multiplication. It's not a swap because the only one that's different is the middle row, and so it must be adding a multiple of one row to another. Well, what happened here is we noticed that the 1 didn't change, so if we did a 0 times that, if we did 0 times anything, that wouldn't have changed the 1. So that's a clue. But however, this became a 0. So it appears that it should be -3r1 plus r2. -3 times r1 gives -3 there, which cancels. -3 times 0 will leave the 0 alone, and so it'll just be 0 plus 1, which is still 1. And then -3 times 2 is -6. Add that to 7, and you do in fact get 1. So that in fact works. A natural question, though, in all of this is, why does this matter? And the answer of why it matters is simply what I said at the start, which is we can now streamline our Gaussian elimination by ignoring the variables. So that's exciting because hopefully this will help speed up that process of solving systems of equations. So this is going to be a bit of a long example, but we're going to go ahead and compare the process of solving a linear system to solving it with an associated augmented matrix. Okay, so again, a warning, this will be a long process. It's not difficult, it's really more tedious than anything else. Here, to start solving this, what we would have is we would take 0. So first we want to eliminate this, as we have before. We've seen this before. So to eliminate that, we're going to take equation 1 and add it to equation 2 to get a new equation 2. So we take equation 1 plus equation 2 to get a new equation 2. That will eliminate the x's, as I said, and we will end up with the top will remain unchanged. X minus 2y plus 3z equals 9. The bottom, once we add, will become y plus 3z equals 5. And then the next one will be, then we would have x, we would then have 2x minus 5y plus 5z equals 17. Next, we would add -2 times the first equation to the third equation to be able to eliminate the y there. -2 times equation, so -2 times equation 1 plus equation 2 to get a new equation 2, or equation 3, sorry. To get a new equation 3, so we would have x minus 2y plus 3z equals 9. Y plus 3z equals 5. And then now we'll have -y minus z equals -1. And then we would go ahead and multiply by, we would go ahead and do -2. We would add adding the second equation to the third equation, equation 2 plus equation 3 to get a new equation 3 will eliminate the y in the bottom equation. So we have x minus 2y plus 3z equals 9, y plus 3z equals 5, and eliminating, we're going to have a 2z equals 4. Finally, we would multiply, so going up here, we would do equation, we would do 1/2 times equation 2, equation 3 to get a new equation 3, which is to say that we would have, what? So we'd have x minus 2y plus 3z equals 9, y plus 3z equals 5, and z equals 2. And now we have this in row echelon form, right? I'll go ahead and make a little dash there. And so since this is in row echelon form, we could actually now solve, if we wanted to, by using back substitution. If you use back substitution, using back substitution, we would have you would eventually get 1 comma negative 1 comma 2. And this is a problem we've done before, okay? And then you should be sure to check, right? However, I want to now focus on what happens with the associated augmented matrix. So the augmented matrix for this would be 1, negative 2, 3, 9, negative 1, 3, 0, negative 4, 2, negative 5, 5, 17. And now what I'm going to do is I'm going to start manipulating the rows. So here, just as I added equation 1 to equation 2 to get a new equation 2 to eliminate the x there, I want to eliminate the negative 1 and make that a 0. To do so, I'm going to go ahead and write it the following way. So I'm going to have 1, negative 2, 3, 9. And again, what I'm doing here is I'm adding negative I'm going to add negative, sorry, give me a moment. I'm going to add, so I'm taking, I did equation 1 to equation 2, so R1 plus R2, and I'll just write it that way. So I took R1 plus R2 to get a new R2. And that's why I point to R2 there. Doing so, I end up with 0, 1, 3, and 5, which I note corresponds to exactly the coefficients there. These coefficients remain the same. And then I just keep going, right, mimicking what I did over here. So this time around, I'm going to take negative 2 R1 plus R3 to get a new row 3. So 1, negative 2, 3, 9, 0, 1, 3, 5. And then in my bottom row, I'm going to have 0, negative 1, negative 1, negative 1. And then I'm going to eliminate that. So I do, to eliminate the negative 1 in the middle entry there in the bottom row, I would take R2 and add it to R3 to get a new R3. That's why my arrow points there. So the arrows point to where I'm, to the row I'm changing. And so I have 1, negative 2, 3, 9, 5, 1, 3. Then I'd have 0, 0, 2, 4. And then the final thing I did was I manipulated the bottom row, right? So I got 9. And what I did to get the bottom row is I just did 1/2 times itself, right? And so doing 1/2 times R3 gave me 0, 0, 1, 2, dividing everything by 2 there. And of course the middle row stays the same. All right. And so that gives you an idea of how this is done through sort of a compare and contrast. And now it's your turn to try out an example. So go ahead and basically repeat the process I just did. On the count of 3, I will reveal the solution. 1, 2, 3. And there is your solution. I will note here that I went ahead and once I got down to here, and I got the zeros where I wanted them in each one, I went ahead and I wanted to get rid of the constants there since I saw clear divisibility. And here, because I ran out of room, I did 2 row operations at the same time. For more practice, be sure to see the textbook, pages 549, 550, and work the suggested exercises. In our next video, we're finally going to do Gaussian elimination with matrices for real this time.